Action.
Hello everyone. We are going to perform the experiment, the study of capacitor charging and discharging, and this experiment is divided into three parts. First is to estimate the time constant for a given RC circuit, and here we plot the graph voltage versus time, and second is to estimate the leakage resistance, and third is to study the adiabatic charging of a capacitor using energy dissipation. And in this we will plot the I square versus time, where the I is the current. In first part, we will try to see how the capacitor is behaving while charging and discharging, and from this graph we will get the time constant experimentally, and this time constant can be calculated theoretical by using a formula, and then we will compare both these values. In second part, we will calculate the leakage resistance. Practically, the resistance of a capacitor is infinite. But practically does not possible, because they do not maintain the charges indefinitely, and therefore there is always a leakage of resistance. In our experiment, you will see that the major leakage resistance is of order of mega ohms, and which is very high as compared to the values of the other experiment presented in the circuit. And in third part, we will study the adiabatic charging. As you all know, that the dissipation energy in the capacitor is half CV square. And is there any way to reduce this dissipation? Yes. Instead of charging the capacitor to the maximum voltage in a single step, if we charge it in a small step, then it can be reduced. And for example, if you are charging it from 0 to 10 voltage, if you do in two steps, like 0 to 5 voltage and then 5 to 10 voltage, and we will see that the value of the energy dissipation it will be reduced almost to the half of the previous value. And theoretically, if the successive step of infinitesimal small values, the dissipation can be entirely eliminated, and this is called the adiabatic charging of a capacitor.
3.
Before the start of the experiment, we should take into account of some precautions. First is to discharge the capacitor before the start of each experiment. Second is the connection must be properly done. And third is to check the values of resistance and capacitance using multimeter, since the resistance and capacitance have been exposed to the environment for a long time, so their values may be changed.
Next, we will move to the experimental setup. This is DC power supply. Here it is on and off button. This power supply is divided into two parts. First one is to control the voltage, and second one is control the current. But in our experiment, we need to control only the voltage. We don't need this current control. So in this, by switching off this, here it is showing the reading, what is the current, what is the voltage supplying to the circuit. So this is the coarse button, this is the fine button. With the coarse button, you can move it like this, and it will increase or decrease the current with large magnitude, like it is 14, then 15, then just 16. But with the fine button, you can tune this current finely, like 0.1, like 4 to this 5, 0.5, 0.6, like 16.6, it going like this. These two buttons are important. Now these are the two nodes where we will see later that how to connect these. This is positive and this is negative. How can we connect with the circuit, main network board? You have to take care of that. After each experiment, you have to switch off this button. Always remember. Now move on to the network board. This is the network board. Here switch S1 and S2 is provided. This is the common node for the S1 and S2. 4 different resistors are provided here, and the 4 different capacitors are provided here. And this is the ammeter, which has least count is 0.01 milliampere. And this is the voltmeter, which has least count is 0.01 volt. This is the list which is here given the values of the resistance and the capacitors. The first resistance, the round of value of the first resistance is 100 kilo ohm. The second resistance is 15 kilo ohm. The third resistance is 10 kilo ohm, and the fourth resistance is 5 kilo ohm. The round of value of this first capacitor is 220 microfarad, and the second capacitor has 1000 microfarad. The third capacitor has 470 microfarad, and the fourth capacitor has value 100 microfarad. This is the This is a multimeter. It is switch off and then it is switch on. Here many options are available here, but we need only this we have to measure the resistance, so this option, we have to measure the capacitance, so this option, and we have to measure the current also. So these three options are other three options are important. Now if you this arrow is on this ohm sign, then it will measure the resistance. If it is like this at the sign of capacitor, then it will measure the capacitance, and then if this is here, then it will measure the current in ampere. If it is at here, then it can measure the current in milliampere, and if it is here, then it will measure the current in microamperes. These are the nodes. First node is the common node, which is negative, or you can say it is ground. You can connect this black wire here, and this one is the when you measure the voltage or resistance, you have to connect this red wire here. When if you want to measure the current, then you have to connect this red wire here in milliampere and microampere. For ampere, you can connect here. Okay. Now I will show you how to measure the resistance by this multimeter. Here, like I have put this arrow sign at the ohm sign. Then see here. This resistance has value 10 kilo ohm. So see, like 10 kilo ohm. Sorry, its value here shown 10 kilo ohm, right? This is stopwatch. This is stopwatch. You can start, then pause, start, and pause, and by this button you can reset this stopwatch. It is this stopwatch we can use to measure the time when like you take in intervals. So you have to measure the interval. What is the interval at the time of measurement? 3.
Now we are moving to the first part of the experiment. This is the circuit that we follow for the which we use for charging and discharging of a capacitor, and these are the convention we are followed. This is the power supply, and this is the ammeter. This is the resistance. This is the electrolyte capacitor, and we parallelly connect the voltmeter to the capacitor. And these S1 and S2 are the two switches. When we switch on the S1 and switch off the S2, the circuit will become for the charging. And when we switch off the S1 and switch on the S2, and the circuit will become for the discharging. And I will show how to make this circuit on a network board, and using this circuit we will measure the voltage alongside with the time, and this is the format of the table.
2, 3.
Now we move to the first part of the experiment, and this is the circuit that will be made on the network board, and these are the conventions we are going to use. And let me see that makes the connection. The positive terminal of the power supply is connected to the positive terminal of the ammeter. Positive terminal of the power supply is connected to the positive terminal of the ammeter, and the negative terminal is connected to the positive terminal of the R, of the resistance. Conventionally, practically there will be no nodes as such positive or negative terminal of the resistance, but for our convention we have taken this terminal as positive and this terminal as negative. So this positive is connected to the negative of the ammeter, and now the negative terminal of the resistance is connected to the positive terminal of the capacitor. And this negative terminal of the capacitor is connected to the common of the two switches. and the negative will be connected, and negative terminal of the power supply will connect to the switch S1. And to make the complete circuit, we also connect the switch S2 sorry, to the positive terminal of the emitter. And we have also connected the voltmeter parallel to the capacitor. So the positive of the capacitor is connected to the positive of the voltmeter, and the negative terminal of the capacitor will be connected to the negative terminal of the voltmeter.
2, 3.
Switch on the main supplies, then the power supply. We set our power supply voltage to 10 volt, and here we can see there are some values in the voltmeter. So we have first discharge the capacitor. And for the charging purpose, we should on the switch S1 and switch off the S2. And for discharging, the switch S2 should be on and S1 should be off. So first we are doing for the charging. So switch on the S1. Here we can see the current is increasing, and current is decreasing, and voltage is increasing for the charging. For the time, we will use the stopwatch, and for each 5-second interval, we will measure the volt in the voltmeter. We start the timer. With the 5 seconds, correspondingly measure the volt reading in the voltmeter. Here we can also measure the current in the ammeter, which can be used in the later experiment.
Go.
I'm giving you the rough idea how to calculate the first part of the experiment. For a given R and C value, the VC versus time graph will look like this. And this is for the charging. To calculate the time constant graphically, we have to observe the half of the value of V0. Suppose V0, we have taken the 10 voltage, and V0 by half will be 5 volt. And suppose 5 is come here. So we draw the line from this, and it will cut some point on the graph, and just draw the normal from this point on the x-axis. And this point will be your time constant. This time constant can be calculated theoretically by using a formula, which is V0 minus V upon my V0 equal to e की power minus t by RC. And by taking the V equal to V0 by 2, this formula get converted into t half equal to log of RC log of 2. And you can compare the theoretical value with the experimental value. And there's another way to do this, and you just you have to do is take the log from on the both side, and draw this log term along the y-axis and this term along the x-axis, and you can repeat this process again and verify the theoretical and experimental value.
Move on to the third part of our experiment, which is to estimate the leakage resistance of a given capacitor. And in order to measure this leakage resistance, we have to have two different setups, which you can see in figure 1 and figure 2. In figure 1, you can see that this RC, that the dot line actually tells us that the RC is not connected to the particular or the actual circuit, but it is a virtual resistance of this capacitor C, which is we have to measure this RC. And for that, we have to first connect the circuit in this way with an milliammeter, and first we have to charge this capacitor fully for a given supply V0. And since this capacitor is not when this capacitor fully charged, it attains a voltage Vc, and then this current will drop from a peak value to the lower value gradually, and then when it shows a zero reading in a milliammeter, then you have to connect this milliammeter by a micrometer, and when you connect this micrometer, you will see that although this shows a zero reading, but it will show some readings of the order of 10 to 20 microammeter, and there will be fluctuations around it depending on the resistance and capacitor you have arranged in a particular setup. After this, you have to calculate the current, this IC around this microammeter, which is called the leakage current, and from that you have to evaluate this leakage resistance RC from the calculation, which I will show later. For that, you have to make the table in this following order. For given V naught, for X volt, for example 10 volt or 15 volt or 5 volt, as per your convenience, you have to connect two C1 and C2 possibility, because there are a lot of connections will be available in the network board, which I will show later. And you have to figure different combinations of resistances, and for each resistances you have to arrange this circuit in this following order. You have correct you have to measure this IC around across this microammeter, and after that we have to perform the calculation, and then you have to measure the leakage resistance for the given capacitor. So now I will move on to the network board. This is the rough idea of what you have to do. As I have explained, for this experiment you have to do two different circuits. First you have to measure the complete the circuit with this milliammeter, then you have to measure the leakage current using this micrometer. But for our convenience, we will take the advantage of this multimeter, and we will complete the circuit using this multimeter only, and we will not consider this millimeter given in the network board. We will consider this multimeter and complete the circuit and take the reading using this millimeter and micrometer option. So our plan is that first, when we connect the circuit and then charge this capacitor, we will first turn off this cursor to millimeter range, because it will show reading in millimeter, and when it will show a zero reading after this capacitor is fully charged, then I will change the cursor to millimeter to micrometer to measure the leakage current, and from this leakage current you can easily calculate the leakage resistance. So let's begin. So let me off this multimeter again, and I will show you how to connect this circuit using this multimeter without using this millimeter that is given in the network board. So first, as you see in the circuit, the positive node of the power supply is connected to the positive node of this millimeter, but here we will be using this multimeter. First, let us switch on this power supply and connect the positive node of this power supply to the positive node of this multimeter. But here we have to focus that we are going to measure the current only. So there are different positive nodes here. So we have to fix the positive node using in this node where millimeter and micrometer is written. Now what we will do, we will connect the negative node, which is here in the common negative node of this multimeter, to the positive node of the resistance. So resistance have no positive and negative node, so it is our convenience that we are considering a 15 kilo ohm resistance, and we are considering this as a positive node and this is a negative node. So I am connecting the negative of the multimeter to the positive of the resistance. Now negative of the resistance goes to the positive of this capacitor. So for our convenience, we will consider a 2200 microfarad capacitor. So the negative of the resistance, for our convenience we are considering this is a negative node, it goes to the positive of the capacitor. Now the negative of the capacitor, as you can see, negative of the capacitor goes to the switch. So the negative of this capacitor goes to the switch. Okay. Now to complete the circuit, we have to connect this node to the negative node of the voltmeter, voltage supply. Since we are also going to measure the voltage VDC around this capacitance, so we have to connect a parallel combinations from positive to the positive and negative to the negative. So positive goes to the positive and negative goes to the negative. So now let's switch on this multimeter to millimeter. Yeah. Now let us switch on this device voltage supply, and we fix for this demo measurement, we fix the voltage around 10 volt. So you can see here there are some small fluctuations around the voltage VDC voltmeter. So we will first short this using a wire. So it is now 0 reading. And moreover, I want to also mention that we are going to measure the DC current. So I have fixed this point here DC. So you can change by pressing this yellow button. So you can change it to DC to AC. So I have fixed it in DC. 3. Now let's switch on the circuit. As you can see, the voltage is increasing and current is dropping. So since we have considered a 10 voltage of power supply, so we will wait till it attains the maximum value of VDC. And then what we have to do, then we have to wait for a time which is much larger than time constant of this particular setup, where I have considered a 15 kilo ohm of resistance and 2200 microfarad of capacitance. So for this combination, once this multimeter shows a 0 reading in the millimeter cursor, then we have to wait for a time, and then we have to change this cursor from millimeter range to micrometer range in order to measure the leakage resistance, leakage current, from where you can calculate the leakage resistance. So let's first wait till it shows a 0 reading and it attains the maximum voltage VDC. So current is gradually going down and voltage is attaining its maximum value. And depending on that, you can actually consider different combinations of capacitance and resistance, and we have to measure the IC for these different combinations. And you can also combine two different voltage combinations. For example, we have considered a 10 volt of voltage supply, but you can also consider 15 volt or so, and then you can also combine this C1 and C2 as your choice, and then you can measure this IC for different resistance combinations. So now, as you can see, it is almost showing a 0 reading. So it is showing a 0 reading. So the point is that we have to wait for a time which is much larger than the time constant of this particular setup. But for our time convenience, I am directly switching this micrometer to the millimeter to the micrometer cursor. So as you can see, although in millimeter scale it was showing a 0 reading, but in micrometer it is showing some reading of the order of 10. So we have to wait for a time while it saturates and it shows a fixed reading, and that is the reading of the leakage current for this particular setup.
3.
Once it saturates this reading, we have to take care of that reading, and you have to do a different measurements for different setup. So that is for this part of this experiment, and we have to repeat the same for different combinations, and you have to calculate the leakage resistance. As of now, we have measured this leakage current IC for a different setup of R, as you can see here, R, and for different choices of capacitance C. So this RC that we have to measure is actually not the resistance that is connected to the Eexp1 network board, but it is the virtual resistance that this capacitor possesses. So the formula to calculate this RC is this: V0 by IC minus R, and V0 is the power supply, and IC that we have measured from our experiment. So for example, in a particular setup, I have considered V to be 10 volt, and my IC turns out to be, for this particular setup with C, around, for example, I consider this 1000 microfarad, and this for particular setup, say my IC turns out to be 1.4 microampere. Okay, so for this particular setup, you will see that this calculations lead to a value of the order of roughly 10 mega ohm. So you see the resistance I have used for this particular setup is 10 kilo ohm here. So for this particular 10 kilo ohm, my resistance around this capacitance turned out to be of the order of mega ohm. In principle, theoretically, this resistance RC has to be infinity, but due to some practical reasons, as this voltage doesn't charge fully and doesn't reach further to the supplied voltage, so this doesn't happen in a practical case. So in practical case, although this RC not turns out to be infinite order, but it's of the very high order given the resistances of the particular setup. So that's it, and you have to verify for different combinations of R and different combination of C, and you have to measure this IC, and you have to verify this claim that this leakage resistance of the capacitor is higher order given the resistances of your particular network setup, and this is how you measure this leakage resistance. The circuit for the third part of our experiment is similar to the what we have connected in the first part of our experiment, which is when we are studying the charging and discharging of the capacitor, and where we have derived this time constant. The circuit is similar, so I'm not going to show how to connect this circuit because it's already there. You can try to learn it. We can directly start the experiment, the third part of our experiment, which is to study the adiabatic charging of a capacitor. As you have already learned that while fully charging a capacitor, the energy dissipation is half of CV square, where C is the capacitance of the setup and V is the voltage provided from the power supply. So there's a question arises whether we can minimize this energy dissipation for this particular setup, and the answer come out to be yes, as we have learned last time, that instead of doing in one step, for example, if we have to charge the capacitor for a given voltage to 10 volts, instead of charging from 0 to 10 volt, if we charge in some steps, for example, if we do in 2 steps, like we start from 0 to 5 volt, then 5 to 10 volt, then energy dissipation will reduce around half of the previous value, and we have to verify this particular claim. And for that, you can see in the power supply, first I have set the voltage to be around 5 volt exactly, and now move on to the network board. Here you can see there's S1 and S2 switch. If I switch on the S1, then it will start charging the capacitor. Now let's start charging the capacitor. I put the S1, but at the same time you have to keep in mind that you have to keep an stopwatch and just put the reset button, and while I switch on this button, you will see reading in the current ammeter, and you have to take the reading from 0 to every 5 seconds of the interval. Now let's start. Check, and similarly you will see the current will decrease and this voltage will increase, and it will go on until it is fully charged. So in the power supply, I have given a maximum voltage of 5 volt. So this capacitance which also show a voltage of which is called as VC, or V voltage around the capacitor, which is around has to be 5 volt. And if this voltage reached its peak value, then we have to wait for a time which is much larger than time constant of this particular setup. For example, in this setup we have considered the resistance to be around 15 kilo ohm and this capacitance to be around 2200 microfarad, and for this particular setup the time constant is around 30 to 40 seconds, and you have to wait thrice times the more on an average the particular time constant of the setup. And then what you have to do, you have to switch off or disconnect the circuit completely. For example, if you can switch off this S1, then it will stop, but make sure that it reaches the peak value, and you have to wait for at thrice the times of the time constant of this particular setup. So this is the first part of the third part of the experiment. Now, as you can see, I have kept in the first part to up to voltage 5 volt. Now I change the voltage to 10 volt by managing the course. So it will change the magnitude in a higher order. So I have to tune this fine tune so that it can go to the 10. As you can see, now it is in 10 volt power supply. Now what I will do, I will again start this switch S1 and I will start taking reading for every 5 seconds. As you can see, the current drops from a very higher value compared to when we charged up to 5 volt. So now it will go on and up to the maximum voltage, which is the possible voltage for it is around 10 volt. So it will go on, and until it's fully charged, we will do the same thing as I have done in the last time. We will wait for a time which is much more than the time constant for this particular setup. And at the end of the day, we will again disconnect this device by switching off this S1 switch, and then we will wait again for some time. And after that, what we will do, we will discharge this by directly connecting these two nodes, or we can discharge by switching on this S2. So if I start connecting this S2 switch, you will see it will start discharging. The voltage goes below and it will go up until it reaches its threshold value, 0 value. And you can, in these two ways, you can discharge these two things. But for this time, I will directly discharge this so that I can go on to the last part of the experiment. Now let's move on to the third part of our last experiment, or the third experiment. So where now I have fixed this voltage to 10 volt. So I will directly start charging my capacitor for this particular voltage. So you can see there's a residual voltage in here. So what we have to do, we have to discharge it. So we can discharge this in this way. You have to just touch these two nodes, and you will see it has discharged. Now I will start the S1 button as previously. So I start the S1 button and I start taking reading of this current, and for every 5 seconds of the interval until this is fully charged. So by fully charged, I mean that it attains the maximum value of 10 volt, and I will wait up till there and I will take the reading for every 5 seconds of the interval. So this completes the third part of our experiment. And what you have to do, you have to take this data and the time, and we have to take the square of this current I square, and we have to plot a graph I square versus t. And for every 3 setups that I have already shown to you, for every 3 data tablets, you have to calculate the area under the curve of the this I square versus t plot, which I will show eventually. After this completion of the experiment, do not forget to switch off this on switch and switch off this power supply as I saw. Thank you. After taking the data for the third part of our experiment, what you have to do, you have to generate a plot of current I square versus the time that we have taken. Now you have to generate 3 plots because we have taken data for 3 different setups. First we have taken data for 0 to 5 charging while 0 to 5 volt, then we have charged from 5 volt to 10 volt, and at the end we have charged from 0 volt to 10 volt. And for each 3 data sets, you have to plot an I square versus time. And for example, if I am plotting for this particular setup 0 to 5 volt, the schematic plot will look like this. If I assume that current is in my x square or y axis and time is in my x axis, then the plot will go like this. And never forget to mention the particular or proper unit for this axis. So here it is milliampere square, and then x axis it is a time second. And not only that, you also mention properly the resistance that you have used for the setup, capacitance used for the setup with proper unit. And not only that, you also not forget to mention the scale of this particular graph. So you can take the scale as per your convenience. Now your job is to calculate the area under this curve. Now how will you do it? You do it by counting the number of squares that lies below this curve. So you have to first define the least count of these small squares around the x-axis and around the same y-axis. For example, is least count on the least numbers is along the x-axis is a unit, and say along the y-axis it is b unit, and you end up counting the number of squares that lies below the curve is around 400 say. Then you have to calculate the area. The area turns out to be n into a into b with proper unit. What you have to do now, you have to calculate the same for the next two parts, and you have to compare the result for setup number 1, setup number 2 and setup number 3, and for them you have to verify that the energy dissipation for the charging of a capacitor is reduced when you charge in a two-step rather than in a one step, and this is what you have to do.